I will go ahead and make you a presenter so you can chat. Ziye Yang is a cloud software engineer at Intel involved in Storage Performance Development Kit or SPDK development work. Ziye's interest in system virtualization, file system and storage related research and development work is what brings him here today. Ziye currently has 15 issued patents in US and 7 issued patents in PRC. It's my pleasure to welcome Ziye to the Day 2 workshop. Ziye,
Yeah,
take it away.
yeah. My name is Ziye Yang. You can call me Ziye, and it is my great pleasure to attend this virtual workshop. Actually, it is my first time to attend this workshop. Um, let's start. My topic is SPDK-based user space MN over TCP transport solution. So how to go to next page?
That's it, your prompt.
Okay, you control right. So please go to the next page. Uh, uh, this page lists the outline of this topic. We will first introduce SPDK MNE over Fabric's development history and the status. And the second part, we will introduce the detailed design of SPDK MNE over Fabric's TCP transport solution. And the third, we listed some knowledges to how to leverage kernel TCP IP stack to optimize the MN over Fabric's TCP transport. Though we also have the user space library integration like VPP, but we think that currently we can utilize the kernel TCP stack with some common knowledge and use it better than the VPP solution. And the first part, we will give some experimental results from our report, which you can download the report from spdk.io website. And the fifth part, we will introduce some ongoing work and our development plan for MNU Fabric TCP transport. Then we will get the conclusion. So please, next page. Next page. Again, thank you. This page just shows the SPDK MNU or Fabric's target timeline. We can see that we released our first MNU or Fabric's target in 2016 with the spec release of MNU or Fabric's RDMA transport, and in 2019. January, we released the TCP transport just after the technical proposal 8000, which is the TCP transport spec defined by MN Express Group. And I want to mention that in this year, in next SPDK release, we will release the user-based transport support. Actually, this is not the user transport is not the specification defined by the MN Express group. It is a specific transport implemented in SPDK, which is a joint work between Intel and Nutanix. And this will be used for those containers or virtual machines. Previously, we used SPDK vhost to accelerate the virtual SCSI or virtual block in the virtual machine. And with the user transport support, we can directly replace the SPDK vhost solution with this new end user-based transport support. Next page, please. And this page just shows the timeline of SPDK MNE or Fabric's host design and implementation history. I think it is nearly seen. In 2016 December, we released RDMA transport, and in 2019 January, we released TCP Transport, and for the end user transport support for the initiator, we will also release it in July's release. So next page, please. This page just highlights the design of SPDK manual fabrics target. I think that the most important thing we want to pursue in SPDK project is about the performance. So we use following rules to design the SPDK and manual fabrics target. First, we use the user space NVMe driver with a synchronized port mode usage, and this will reduce the overhead for each NVMe I/O according to our experiments. Compared with the kernel NVMe driver solution, we just compare the driver performance. SPDK's NVMe driver is about 6 to 10x better than kernel solution for the per CPU core performance. And definitely we utilize this in SPDK NVMe or Fabrics target. We build a user space IO stack relied on this use-based NVMe driver, so the performance is very good, especially for the RDMA transport. And secondly, we use the SPDK-based framework to do the code design. In each SPDK thread, we will use group polling manner. It means that each SPDK thread will be responsible to handling massive connections with the polling group. Thus, for example, for the reading event on all the connections, we can just use one function to get which connections are active. Then we can handle these connections efficiently. And the third part is that if a connection is accepted by the SPDK manual fabrics target, we will use the algorithm to dispatch this connection to the specific SPDK thread. Then the SPDK thread will be responsible for all the lifetime of this connection. Then there will be no resource contention among the connections. For example, among the connections on different CPU cores. So it is very efficient. Second, the fourth is that all the NVMe command on the target side, we use a synchronized way, and there is no locks on the data path. So the performance is really good. So compared with the kernel solution, if we use the RDMA transport, the per CPU core performance for IOPS SPDK solution is still 6 to 10x better than kernel target. And if we use the TCP transport, the per CPU performance, the per CPU core performance for IOPS is about 1.5 to 2.5x better than kernel, because we even with SPDK's user space IO stack on the NVMe drive, I mean on the backend storage, but we still use the kernel TCP stack. So the performance benefit is eaten by the kernel TCP IP stack. Though we tried with some user space stack like VPP, but we didn't change it more. So next page. So we will focus on the NVMe over Fabric TCP transport optimization in SPDK. So next page, please.
Ziye, we have a question from the audience. Can I,
Yeah, please.
are you able to? Okay. This is a question from Doug Ledford. Who's on unmute right now. Doug, do you want to go ahead and ask your question?
Yeah, please. Yeah.
I was just curious, since the design you put up on the screen had connections pinned to specific CPUs in order to get rid of the locking contention and everything else.
Yeah.
What happens if
Yeah.
you have an unruly load? Like if you have a lot of data coming in from hosts that happen to be pinned to the same CPU while you've got other CPUs that are setting idle, do you end up overloading that one CPU core while other CPU cores set idle?
Yeah, this is a good question. Actually, this is the connection scheduling algorithm. Our default scaling algorithm is the round to robin. So it means that if, for example, if you have 4 CPU cores and on each CPU core there is a SPK thread, then it means that if there a connection is coming, we will use a round robin manner to choose the CPU core or SPK thread to run. So the load balance is very good. And also
But
currently,
that's done
yeah,
at connection time. What about after connection time? I assume the connections are long lived.
yeah, you have a good question. The next is the issue we just want to solve in SPDK. Currently, SPDK thread can be dynamically migrated among CPU cores. So in last maybe in the 1907 or 10 release, we just discouple the SPDK thread and the CPU core. So we will soon design the dynamic migration uh, strategy. So it will solve the questions you ask. It means that we can dynamically migrate SPK thread to different CPU cores. Since currently we already decouple the SPK thread to the CPU cores, the polling groups are belong to the SPK thread, not the CPU cores. So we can easily migrate the SPK thread to a new CPU core if there is the load balance is not good as you described. So I think it will definitely solve the questions you ask. So this is my current answer. But definitely this migration feature is not ready in SPK yet. We just decouple the SPK thread with the CPU core.
Okay. Thank you, Ziye.
Yeah, you're welcome. So this page just shows the general design and implementation. We can see that SPK support 3 transports, and under the TCP transport, we use different socket implementation. We call the 3 implementation as POSIX, URIN, and VPP. The POSIX, it means that we just use the POSIX API in Linux to use the socket. And the second is the URIN. We just use IO URIN from the storage to network to utilize to efficiently utilize network. And absolutely, this is a very new feature. I mean the IO URIN. You need both the IO URIN library in user space and the kernel support. But we already released this feature in in this year's last release. I mean the April's release. But we will continue improve it. And the third is the VPP. The VPP is also released, but currently we see the performance is not good as we expect. So we have an announcement that we will disable the VPP related test in SPDK's 20.7 release, and we will remove the VPP related socket API support in 20.10. I mean in this October. So next page, please. So this page just shows the performance design consideration for the TCP transport. I think it is similar to the general SPDK manual fabrics targeted design. But I think I want to emphasize is that currently we use the kernel TCP IP stack, but we use the encapsulated socket API. It means that if you have the very high efficient use space TCP IP implementation, you can easily plug your use space TCP IP socket implementation into SPDK's encapsulated socket API with just implement all the function pointers. And for the third and fourth part, we all use the state machine to track the life cycle of the PDUs or MNE TCP requests in each connection. So it is very efficient, and also the code is very readable to the developers. So next page, please. This page just shows the MNE TCP PDU receiving. We just use the a state machine just follows the MNE OR Fabric's TP 8000 spec. So this is just follows the spec, and if you read the code in SPDK, you can follow this diagram. I think it is better for you to understand the code. So next page, please. This page shows the state machine to handle the MNE IO for each connection on the target side. We just create several states like the MNE TCP request is free, is new, is waiting for a buffer, or the other status. I think that if you want to deeply understand the SPDK MNE TCP transport implementation, if you read the code, you can just use this diagram, and it is very very good for you to understand all the code in SPDK's TCP transport implementation. So next page, please. Under this part, we will just want to share how to smartly use the kernel TCP IP stack, especially to describe our implementations in POSIX or using using API. So next page, please. Oh, this page is just the information I mentioned before that. Here I want to emphasize it. For SPDK's current design, especially for the TCP transport, we will focus on optimizing the TCP transport with the kernel TCP IP stack with the two solutions, POSIX and ULIN. Firstly, we will recommend the POSIX implementation since it is very stable and there are no requirements on the kernel. But if you want to see much better performance, you can use the IOULIN socket implementation, but it requires some dependency for your kernel and IOULIN library, and this is experimental since we know that the IOULIN development is still in progress, and we will see that there will be the great improvement for IOULIN in the future. So we think that though currently we recommend the POSIX, but we think that the ULIN will be the future to efficiently use the kernel TCP IP stack. So next page, please. So this page just the common knowledge to smartly use the kernel TCP IP stack, which we summarize here. And this is what we do in SPDK. For example, for the socket descriptor, we will use the non-block setting on the file descriptor. Then it will match the SPDK's polling framework. And the second is that in each SPDK thread, we have a group, and we use group-based strategy on polling or read-write for many connections. For example, if we want to track the polling event of all the connections, we can just use the ePoll strategy in POSIX implementation, and we can use the polling strategy in URI implementation. So it is very efficient. And also for the write-v asynchronous support in our URI implementation, we just use the IO based submit IO submission. So for example, if there are 16 TCP connections in the group, we can just use one CPU, one system core in one round, and reduce the system core overhead for each connections. And a third is that currently we can ping the SPDK thread in a dedicated CPU core. Currently, the migration is not supported, but we will support it in the future. And also for each read operation on socket, we can use the buffered read. And there will be some diagram to illustrate this in the next pages. And the last is that we merge the write request from the application, and it will be very efficient. Also, it can reduce the system core and improve the throughput for each connections. Each connection. So next page, please. So this page just shows the original TCP read operation on each socket. It means that if there are multi buffers, you need to issue several read system calls. Since in the beginning, we may not know the buffer address of the buffer 1, buffer 2, or buffer 3, so we cannot construct one IOV. So it means that the several real system calls are needed. But we can use another strategy, which is currently used in SPDK. Next page, please. In SPDK, we just implement a pipe library in SPDK utility library. Then we can just use a temp buffer, a very big temp buffer, for example, 8K or 16K to read the data from the kernel with one system core. But definitely, we need the memory copy to the destination buffer. Since for the some buffer usages, we need to use the DMA the memory must be DMA'd, so we need a copy. But we think that if we want to efficiently use a kernel TCP stack, we need to reduce system core overhead. And in SPDK solution, we find that this is very efficient. But definitely for the memory copy, we can also eliminate this. For example, on Intel's platform, we can use the IOAT driver, that is CBDMA, to eliminate the memory copy by CPU, and it will also improve the performance. Next page, please. This page just shows the merged write support in SPDK. It means that we can merge a lot of write requests in the same socket with one big IO vector and issue one system call. Undoubtedly, we can know that for the write, write operation. If we use the non-block mode, there will be partial write case. For example, shown in this diagram, it shows that the first vector is already finished, but for the second element, it just finished half. For the third, it is not finished. So in our implementation, we also handle this issue, and we will make it very efficient with our approach, since we will cyclically reuse the big IO vector. So next page. This page just shows a group-based synchronous I/O operation with U-ring. You know that there are many connections in the same group. So we can so for each connection, it will prepare the right V, and we can just use the one system call to submit. For example, previously we have the libaio support to use the network, and the second is the U-ring. Finally, we choose the U-ring, so we can use one system call in one round to submit all the write V's from different connections to the kernel, and this code is ready in SPDK. So next page, please. So previously we talked about some design, and in this part we will share some performance results. Next page, please. This page just shows the latency comparison between SPDK and the kernel solution with the non-BDEV, with the Q depth equals to 1. And you can view this report from SPDK's website. Currently, the report version is 2001, and we will have the new performance report soon. From this diagram, for left side, we just deploy the kernel initiator on the initiator side, and in the target side, we use the SPDK or kernel target, and we can see that if we use SPDK, we can reduce the latency for different workloads at least 30%. And the right diagram, we can see that if we use the SPDK target on the target side, and we use the SPDK initiator or kernel initiator, we can see that if we use SPDK initiator, we can still improve the latency at least 30%. So next page. If we combine the two diagrams into one diagram, it means that we just compare the end-to-end latency between the kernel solution and the SPDK solution. We can see that the end-to-end latency solution from SPDK is much better than kernel. It improves the latency at least 60 to 70%. So next page, please. And this page just shows the per core IOPS comparison between SPDK and the kernel. We can see that generally with the connections increasing, the SPDK performance is about 1.7 to 2.4x better than kernel. I think I already explained that. Kernel TCP IP stack is the bottleneck. We try to improve the performance, but according to our analysis with the performance data, the most CPU time is consumed on the TCP IP stack. So this is why if we use the RDMA transport, the CPU core performance is 6 to 10x better than kernel. But for the TCP transport, we just get 1.7 to 2.4x better. So next page. In this part, we will describe some ongoing work with SPDK. So next page, please. The first part is that we will use the Intel's ADQ feature, that is application device queue feature from Intel's Ethernet 800 series network adapter to improve the IOPS and tail latency in SPDK, especially for the SPDK MNU fabrics TCP transport. Definitely, this requires the new Intel's 100 gigabit NIC and also the kernel support for the ADQ feature. And currently, we want to see that this development is in a good progress in SPDK. And when Intel's 100 gigabit NIC, for example, the 810 NIC is released, we will soon release a similar feature. We will soon release software features in SPDK and to better use Intel's 100 gigabit NIC. And next page, please. Besides that, we will continue the development of SPDK's MNU fabric TCP trend in the following part. For example, we will continue the functionality test with Linux kernel solution. And absolutely, for the performance, we are still care. It is our focus. So we will pay attention on how to use the IOU ring to improve their TCP IP transport and improve the performance. And also we know that many companies or customers, they like to use their hardware offloading. So definitely we will also pay some attention in SPDK to how to guide the hardware vendors to offload the TCP workload in smart NIC or in the normal Ethernet NIC. So next page, please. So this is the conclusion part. Next page. Thank you. In today's presentation, I just introduced the SPDK's MNU fabric solution, and especially the detailed design and optimization strategy or methods in SPDK, and we also share some performance results with SPDK's MNU fabric TCP transport solution based on the 20.01 release. And undoubtedly, we will continue for the MNU fabrics spec and improve our SPDK MNU fabric solution. And the last part, we are welcome to any participation in SPDK community. For example, the bug report or idea discussion or patch submission. SPDK is an open source project. We hope that many companies or individual contributors can participate in it. This is all my presentation today. Thank you.
Thank you, Ziye. Any questions from the audience? You guys have two options to raise a question. One, you can use the Q&A panel to submit a question to me, in which case I will read it, or you can even choose to raise your hand so that I can give an opportunity for you to interact with the speaker. We do have a follow-up session later today by Seth Howell talking about SPDK and how to optimize it for the NVMe over Fabrics RDMA stack at 9 a.m. So it's a nice follow-on. Ziye, I know you're in a different time zone, so thank you for making this happen for our OFA community.
Yeah, thank you. Thank you to give me the opportunity. Thank you.